screen. Very good. Thank you so much again for joining us today. As Michelle said, my name is Andy Erickson. I'm very excited to be here. I'm very honored to be invited to give this webinar on the threat of climate change to urban stormwater infrastructure. This was some work that we've done over the last several years, and we're continuing on to it. But as we saw in the poll, it's not news to many. If you do just a search on Google for extreme weather, this is something I just did last night, and I pulled up, dozens of stories within the last 24 to 48 hours. And it's not a local problem. It really is a global problem. We're seeing it all over, but we do see it in news where we're living, and it's affecting all of us. And it has some strong impacts in many different ways. So extreme precipitation, in terms of wet weather, large events, but also extreme droughts. We're seeing more droughts. We're seeing hot weather. We're seeing mild winters. We're seeing changes in our freeze-thaw cycles for those of us that live in cold climates. So it's very, very challenging. And in some places, people are asking the question, is extreme weather the new norm? Is it something that we need to get used to? Is it something that we have to adapt to? And arguably, when we see disasters based on extreme events, many places, many jurisdictions, many decision makers are saying, yes, we need to adapt. We need to change what we're doing to be more resilient. And in fact, there's even funding strategies coming through to help build more resilience into our urban and civilized infrastructure. And as I said, it's not a local problem. It's not only affecting a few, it's affecting many. Even in the arid Southwest, heavy downpours are expected to increase by upwards of 5%. If you're in New England or in Southeast US, you might be a 70% increase or almost a 30% increase. Where we are in the Midwest, we're looking at somewhere between 30 and 40% increases in the largest storm events. So this is kind of the background of where we're coming from and why we started to do the research that we're doing. So what we're doing and what the research we've done is based on really general circulation models, global climate models, global circulation models, GCMs is the acronym, but it does get different definitions depending on who you talk to and what literature you read. But the foundation of these GCMs is really an assumption about greenhouse gas emissions. That's the foundation of many of these models, and they're using that information to predict or try to project what's going to happen with temperature, with rainfall, and with other climate responses. So really, it's a projection based on greenhouse gas emissions. And really, arguably, our understanding of global weather and global climate, even national weather and climate, I would argue there are things that we don't know. But we are advancing, we are learning, we're using new technology, we're using satellite technology to give us better estimates of what's happening on the landscape and what then could happen in the near future. This is more looking at the long-term future, which, as you can see, arguably, the different pathways are highly variable. The response and the variables, the temperature, rainfall, and other climate is highly variable. So what we did is we wanted to focus on, through funding that was provided from the state of Minnesota, to look at what can happen in Minnesota. And it is looking into the future, but we started with looking at historical and current climate conditions. And we modeled, as you'll see in a few moments, in 3 different watersheds. We looked at the 2-year storms all the way up through the 500-year storms, looking at TP40, which is data from about 1940 to 1960, depending on where you are. Atlas 14, which is kind of the current standard of historical data, of recent historical data, and that was published from 2006 to about 2018, depending on where you were in the country. It came out in different volumes, and that's looking at more recent, more like the last 30 years of historical data up to about 2005 or so. And then we did use some of these GCMs to look at near century, mid-century, and end of century projections of these storm events. And this plot on the right side of this slide here are all of these storms. And this is for Duluth, Minneapolis, and Rochester, Minnesota, which we're going to look at in the next couple slides, these particular watersheds. And they are sorted from the smallest events to the largest events, regardless of whether it's TP40, Atlas 14, or GCM future predictions. And there were some very interesting trends that we saw in this data. Along the horizontal axis here is the storm depth in inches. And I'm going to highlight a couple of these interesting findings. Number one, when we looked at the small events, the 2-year event, the 10-year event, these are events that have a relatively frequent occurrence. A 2-year event, has a 50% chance in any given year of happening. A 10-year event has a 10% chance in any given year of happening. So on the long term, and when I mean long term, I'm talking thousands of years, on average, it should happen. A 10-year event should happen every 10 years once. That's how the statistics and the probabilities work out. But when we look at those small storms, those relatively frequent storms, the Atlas 14 storm depths are actually less than the older historic TP40 storms. In other words, small frequent storms that are happening today, at least in Minnesota, are smaller than the small frequent storms that happened prior to the 1960s. In other words, and actually the opposite is also true, and I'm going to have a bottom line here in a moment. The opposite is also true for the larger storms, for anything that was 25-year recurrence or larger, 25-year, 50-year, 100-year, 500-year. The old historic events prior to 1960, reported in TP40, are actually less than the current historical storms, Atlas 14. Now, everything historic is still less than what the GCMs are predicting for the future, but the bottom line here is today, small storms are actually smaller, and the big storms are actually bigger. So we're still looking at what are the overall annual, are there any annual changes in total precipitation? Or is it just a redistribution of the rainfall? Are we getting more big storms and bigger storms, and then at the same time having fewer small storms? The other way to think about that is frequency. So small storms are smaller today, big storms are bigger today. Another way to think about it is small storms are less frequent. We're just seeing fewer of those small storms. And we're seeing more of the big storms. They're happening more frequently. Now, you can't say the same at the same time. You can't say the bigger storms are bigger and more frequent, because it's all about recurrence interval and storm depth, and you have to have a frame of reference. But no matter how you say it, whether the big storms are bigger or big storms are happening more frequently, that's a problem for us as stormwater managers and decision makers, is we have to deal with this challenge. And what was really interesting is if you think about recurrence, for anybody that's a hydrologist in the room, or think about return interval and things like that, one of the very interesting things is in TP40, the 50-year storm, as I said, has on average in the long, very long term, only a 2% chance of happening in any given storm. 2% chance under TP40 historical record. That storm is now less than a storm that's projected to happen every 4% chance in any given year. So in other words, we've actually more than doubled our probability of having these big storms. And that's also true when you compare the 100-year storm and the 50-year storm from TP40 and Atlas 14. What used to be a 1% chance is now greater than a 2% chance in any given year. So that creates big challenges. We're going to see these big storms more frequently. And if we just think about the change from data prior to the 1960s to what we see today in Atlas 14, again, not even thinking about the future yet, the 100-year event, the storm that has a 1% chance of happening, is somewhere between 20 to 30 or even 40% larger today than it was prior to 1960. And if you read the news, if you do some of the news searching that I showed you at the very beginning, We're seeing storms that are 500-year storms. We're seeing 800-year storms. So even designing or considering the 100-year event is less than what we're actually seeing in our landscape. And that's scary. And it makes us wonder, do we have to think about that? Do we have to plan for that? Can we even consider designing for a 500-year flood or a 1,000-year flood? It used to be that this would happen, it'd be in the news and you'd hear about it and you wouldn't hear about it again for a long time. We seem to be hearing about these very low frequency events happening every single year in different parts of the country and the world. So it makes us wonder, do we need to adapt to very low frequency, very improbable storm events? And so that's what we were looking at for our municipalities in Minnesota. Again, this is funding from the state of Minnesota. So we wanted to look at what's going on in Minnesota and what do our stormwater managers and decision makers need to consider as we move towards the future, as we take opportunities during street reconstructions to build in better and more resilient infrastructure. But it applies elsewhere. As I said at the beginning, this challenge is not unique to Minnesota. It is not a local problem. So you can learn from what we found in our general observations. And again, what you're going to see in this modeling is we did not look to develop a plan for just these watersheds. We kept it generic and used these model watersheds in Duluth, Minneapolis, and in southeastern Minnesota, Rochester, Minnesota, as a surrogate, as an example for other watersheds in Minnesota and beyond. And that's because these watersheds are mixed urban spaces. In Duluth's Miller Creek subwatershed, the lower part of the watershed is actually part of downtown Duluth, but the upper part of the watershed is relatively rural and even undeveloped. We only have about 23% impervious area in this subwatershed. And much of the upper part of the watershed that's undeveloped is the quintessential Great North Woods of Minnesota, those pine forests and undeveloped forested lands. So it's a mixed watershed. And even the downtown Minneapolis watershed, this is one northeast subwatershed within Minneapolis. It borders on Columbia Heights, the city of Columbia Heights, which is a suburb in the Twin Cities area. We're close to 47% impervious in this subwatershed, but that's actually not totally accurate because about 10% of this subwatershed, right in the middle, is the Columbia Heights Golf Course. So it has very, very low impervious area. So in fact, when we say 47% impervious for this subwatershed, really most subwatersheds like this are even higher than that. And Rochester's subwatershed is about 17% impervious, but being in southeastern Minnesota, in this particular subwatershed, the eastern portion is part of Rochester, the city of Rochester, commercial, industrial, and a fair amount of residential subdevelopments. But then really the western half of this subwatershed is all agricultural. So we picked these subwatersheds intentionally to represent the diversity of developed and partially developed subwatersheds that you might see throughout Minnesota and in the rest of the country in North America, where we have some mixed urban centers with residential areas with either ag or undeveloped forested landscapes. And so what was really interesting is even though we saw variability between the watersheds a little bit, the overall conclusions actually came out very, very similar. So we looked at different adaptation strategies. We modeled all of those storm events I showed at the beginning over these three watersheds. And then we asked the question, what can we do about it? We recognized very quickly we were seeing flooding in our watersheds. And so we looked at different adaptation strategies. And there's a lot of details here. And I'll make sure that Michelle and David have the PDF of this document so you can get access to these slides. You can also reach out to me directly and I'd be happy to send you a PDF of these slides so you can get all the details. But I want to summarize this into very simple, different strategies. We first looked at the existing infrastructure. What was in the landscape today? And keep in mind, much of that urban infrastructure is not only old and aging, falling apart, but most of it or all of it was actually designed based on TP40 rainfall records. So it's undersized for even the rainfall we're seeing today, and it's aging infrastructure. But that's what the cities have to deal with. That's what you're dealing with. That's what you have in your system right now. Nobody has enough money to replace their entire system today. But we're working towards that. So then the other adaptation strategies we looked at to try to mitigate the flooding we see is we said, well, what about more storage? Can we put in more holding capacity of this water, hold the water back, slowly release it, and minimize our flooding? We also, because this is being adopted in many places in the US and around the world, wanted to consider smart storage. And smart storage is where you take a storage facility and you equip it with an actuated flow control that's connected to a computer that automatically and in real time continuously will look at the weather forecasts and then make decisions based on an algorithm of whether or not to open this actuated valve and flow control. And most of these systems are designed to do is that prior to a rain event, if we have, let's say, an 80% chance of rainfall and we know we're going to get a half an inch of rain or more, then this smart algorithm would automatically open a valve 24 or even 48 hours before the rain to draw down some of the permanent pool, if there's a permanent pool storage system. And that's where smart systems really have value, is on these systems that hold water back. These wet ponds, these storage systems, even constructed wetlands can be controlled this way. And the idea is if we draw down some of that water, we have some additional storage capacity prior to the event occurring. So that's what smart storage is all about. And many of us know, especially in the stormwater industry, that green infrastructure is a big deal, and we're using it in many of our urban landscapes. Many people say, you know what? Green infrastructure can't help with extreme events. It can't help with flooding. And we don't believe that. So we said, let's model it. Let's see what we can do with these systems. And of course, the old adage, the old historic solution to more water was bigger pipes. Let's just get the water gone faster. So we modeled that to show really what is the difference between these different adaptation strategies. So on the first, and again, there's way more details and data than I can share in the time that we have together today. So I encourage you to check out the final report for this project. You can see the link here. I'm actually going to drop this also in the chat. There are several links there that you can get access to it. I encourage you to check that out and look into the details if this is interesting to you. But one aspect of flooding is depth. How deep is the water? And in modeling terms, it's called node depth. And what you're seeing in the plots is different locations and different adaptation strategies and different storm events in our different watersheds, Duluth, Minneapolis, and Rochester. And the black dashed line that you're going to see on many of these curves are in this particular location, in this node. This was an area where, for example, we might be overtopping a roadway, or we might be flooding really important infrastructure. It was a flooding criteria that we do not want to exceed. And the first thing we noticed in our modeling of these different storm events is many points within all of our watersheds are predicted to flood for just the 10-year event. So even relatively frequent events, 10 years, 25-year or 50-year, I'm not talking the 100-year. Yes, the 100-year flooded, but even the 10-year events were causing flooding of important and critical infrastructure in many of our watersheds, and even under TP40, not even Atlas 14. But when we looked at different adaptation strategies, if we equip our watersheds with smart storage systems, you're going to see it in the presentation today as ponds, but wherever you see ponds, I want you to think storage, whether it's above ground storage in ponds or wetlands, whether it's below ground storage, doesn't matter. It's holding the water back. And if we use smart systems to preemptively drain those down to increase the amount of optimal capacity, those are the most effective at least reducing flood depth in these watersheds and for these storm events. But storage systems by themselves are also highly effective. When we looked at the hydrographs, it's really interesting because there's peak flow, which has damaging impacts, but there's the timing of it. Much of our systems, these peak flows of our hydrographs overlap, and that's where critical infrastructure can fail quickly. Obviously, if we have bigger pipes, we get the water moving faster. That increased our peak flows by upwards of 30%. But what was really interesting, this was no surprise, that's exactly what they're designed to do. But what was really interesting is that it actually caused flooding within our own watersheds. So it wasn't even, it was causing problems downstream, obviously, but it even caused problems within our watersheds. Our system simply could not handle the increase in flow. There are restriction points throughout the system that then flooded because we increased the flow through the system. So pipe upsizing really is not a good thing. It made it worse overall. Again, more storage and smart storage not only delay those peaks, but they reduce those peak flows, and they did mitigate much of the impacts from these extreme events. But even after looking at these 6 different strategies and all of these different storm events in different watersheds, at the end of the day, none of our adaptation strategies prevented flooding. We couldn't fix the problem. We couldn't engineer our way out of this problem. And that's kind of a bleak outlook for our municipalities and decision makers. It's not exciting to get to the end of a research project and say, you know what, none of it solved the problem, but it creates more questions. And there are still many things that we can learn from them. I'm not saying there's no hope, and that's what the rest of our presentation is going to talk about. The next question, if none of our strategies work, then what would it take? How would we need to change our methodology, our design methodology, our decision-making processes? What would it take to future-proof our watersheds? And the first thing to keep in mind is our current standard today, typically, if I generalize, is that most of our stormwater design guidance says roughly 5% of our watershed area needs to be stormwater control measures, okay? 5%, 1 acre out of every 20 acres needs to be stormwater infrastructure for the purposes of water quantity, also water quality. Most of my presentation today is all on water quantity, but water quality is a very important factor as well. But typically, most of our design guidance says 5% of the watershed. And that's the total watershed, not the impervious area. The total watershed needs to be stormwater design. But if we want to mitigate flooding fully, and let's say we want to go big, we want to say, let's mitigate the 100-year event for Atlas 14, our current design precipitation standards. If we are going to do smart storage system, 9% of our watershed needs to be smart storage. 1 out of every 11 acres needs to be smart storage. If we're just going to use the typical storage, not smart, it's just holding the water back, 12% of our watersheds need to be stormwater ponds, effectively, if you want a visualization. 1 out of every 8 acres, 1 house out of every 8 houses in a residential neighborhood needs to be taken down and converted to a stormwater pond. If we want to go to green infrastructure, 25% of the watershed needs to be green infrastructure. 1/4 of all of our neighbors, wherever we live, that space needs to be removed and converted to green infrastructure. That's a major shift in our design philosophy. But you might say, well, the 100-year event, how could we even hope to contain a 100-year event? That might be a little beyond realistic. So let's go to the 10-year event. I already showed you that even under TP40, many of our watersheds are flooding under the 10-year event. Well, if we do storage systems, then again, between smart storage and not smart storage was really very little difference. On average, it was about 5%. So then it matches. It actually makes sense. However, I don't think most of our designs are looking at the whole watershed. Many of our designs are only looking at the contributing impervious area. So in fact, we're going to need to make these systems even bigger. And if we go to green infrastructure, 12% of the watershed, 1 out of every 8 acres needs to be green infrastructure for us to mitigate just the 10-year event under Atlas 14. And that's a pretty tall order as it is. I'm going to summarize kind of these findings, and because this green infrastructure thing became a question for us. And when we compared all of our strategies, as I said, the smart ponds or the smart storage systems, the more storage systems, which is equivalent to underground storage, those were the best in terms of mitigating flood. But we also considered cost. And I'm not going to show you the cost data. It's all in the report. Please go in and look at that. But in considering cost, obviously the lowest cost option is do nothing, the baseline option of using the existing infrastructure. But we know it's aging, we know it's undersized, and we're still going to have to maintain it. And I'll come back to cost at the very end of the presentation. But actually considering costs, smart systems, smart storage systems, and extra ponds are actually also cost effective. So the extra storage and the smart storage were among the top 4 in both flood mitigation effectiveness and cost considerations. But when we looked at green infrastructure, when we looked at infiltration basins, we kind of scratched our heads. It's like, why is this so poor in this analysis? Why is it not effective? We know these systems work well. So why is our modeling not reflecting some of our understanding in our watersheds? And it made us ask the question, is our modeling correct? Is there something about our assumption that's specifically hampering or holding back green infrastructure from appearing to be an effective strategy? And it's all too often when I'm doing research that this is my face. I'm looking at the data and looking at the analysis and drawing conclusions from it. And I'm sometimes frustrated with what I'm learning and seeing in this. And it makes me think, wait a minute now, are we basing our understanding of what's going on here on perhaps faulty assumption or weak assumptions? And the first assumption in this whole process is the distribution of rainfall. So this is the MSE3 rainfall distribution. This is a distribution that's included in Atlas 14. All it is showing is essentially how much rain falls over time, in this case, over a 24-hour period. And you can see in the beginning of the storm, in the first 5 to 10 hours, it's a relatively small amount of rainfall, but then it quickly ramps up and you have a large, heavy, high intensity rainfall for the middle part of the storm, and then a relatively low intensity at the end. What's interesting, if you look at the distribution, if you look at some of the numbers for this, 90% of the rainfall falls within 12 hours of a 24-hour storm. 90% of the rain in 50% of the time. If we zoom in more, 80% of the rain falls in just 6 hours of this storm event. 80% of the rainfall in 25% of the time. And in fact, if we zoom in on how much, we take half the rain event, how long does it take to fall? Roughly 1 hour. 50% of the rain in 1 hour out of 24 hours. This is a very intense part of the storm. And in fact, looking at all 3 of those kind of breakdowns, you can see that much of the rain happens right in the middle. And if you compound that by most of our storm systems are designed with about a 20-to-1 ratio of contributing area to stormwater infiltration area, this intensity gets multiplied by a factor of 20. So that large intensity becomes a very extreme intensity. And we shouldn't expect our rain gardens to infiltrate that quickly. And actually, in some design guidance, restricts our infiltration practices from infiltrating too quickly. So we modeled this and we looked at this MSE3 distribution in these watersheds, and we found on average 30% of the total rainfall, about a third, 33% of the total rainfall actually infiltrated in our pervious areas, not the rain gardens. Only about 8% infiltrated in the rain gardens, but about 60% was runoff under this distribution. Okay, this is what an urban watershed can look like under an MSE3 rainfall distribution, somewhat regardless of the size of storm. Okay, this is more about the intensity. But we said, well, what if we shift that intensity? What if we go Let's go to the far end of the other extreme. Let's go to a uniform distribution that assumes a constant rainfall over the entire 24-hour period. So instead of having a peak in the middle, it rains constant over that entire 24 hours. That's our uniform distribution. Arguably, that's not real. It's not common, but we wanted to see how much of an influence does this rainfall distribution have on all of our assumptions coming out of the results. And when we did that, we saw major shifts in the distribution. 80% of that rainfall, no other changes. It's still a 100-year storm. It's still a large storm depth. All we're changing is how quickly that rain falls. 80% now infiltrates in the pervious areas. That's 132% increase of infiltration just in our green spaces, our lawns, our parks, our neighborhoods. We saw almost a 40% increase in our rain gardens because our rain garden infiltration capacities can handle lower intensities. And we saw over 80% reduction in runoff just by changing one design assumption, the precipitation intensity. So that now has led to a new research project we're working on right now, where we're looking at how do real storms compare, because we see this in the real world outside of the modeling. This is that same MSE3 type distribution you can see here. This is now showing 6-minute intervals, breaking it down to every 6 minutes, and showing that peak intensity of almost 12 inches per hour in that middle 6 minutes of the 24-hour distribution. We looked at a storm that happened in Duluth, Minnesota in 2012. And for comparative purposes, there's no intensity anywhere near that. We have 1 minute intensities, 15-minute intensities, and actual hourly intensities shown here in black, green, and red. And then the cumulative rainfall in blue over about 2 days. And even though this storm in Duluth is estimated to be somewhere between a 600 and 800 year recurrence interval, it still is nowhere near as intense as our MSE3 distribution. So we are looking right now at what are some real rainfall patterns. We have more recent data that's much finer resolution, 1 minute data, 10-minute data, 15-minute data. We're going to look at those distributions and see how far do they deviate from our design standard of an MSE3 rainfall distribution. So stay tuned on that. We can hopefully have more data to share with you on that soon. But overall, what did we learn? I'm gonna move into our conclusions here, and what have we learned from this work? Well, one of the things we learned at first in this modeling is that many of our current models are actually not calibrated for these large, low-frequency extreme events. When we started this project, we thought it would be relatively easy to get a model from many of these jurisdictions and be able to start using it for our analysis. But as soon as we ran some of these big storms, we found that the predictions did not match reality. We saw flooding in areas that nobody had really observed flooding before, even though we've had 10-year, 25, 100-year events in these areas. And that quickly told us that the models are only really calibrated for 10-year events and smaller. And that's because it can be a good relative comparison. It can tell you if you do this or you do that or you do this over here, what are the relative improvements, but it doesn't give you a predictive accuracy. And many of our overland flow paths are not represented well in the models. Water is going to flow through the path of least resistance. It's going to find the places where it can go to get out. And if we're not modeling those areas, those flow paths in our models, then our models are not going to predict reality very well. And actually, this has led to some other research that our PhD student is working on right now, which is taking LiDAR data, which is actually pretty accessible in many areas, and using it. He's developing an algorithm that'll use LiDAR data to automatically create flow paths and channels out of urban landscapes that may not be currently reflected in our SWIM models, and therefore integrate them into SWIM to better represent what happens under these extreme low frequency events. So this is a animated clip of some of that work that he's done already. He's taken LiDAR data, he's created this three-dimensional plot of where the water is, where the water goes, how deep the water is, and how it gets from one point to another. We also saw, as we just saw in the last couple slides, that the Type 2, which is out of the TP40, and the MSC3 out of Atlas 14, really disadvantages anything that infiltrates water. And so when we're thinking about the benefits of pervious areas, green infrastructure, and anything that infiltrates, our design assumptions, our modeling assumptions will strongly impact our interpretations of those results. Out of our adaptation strategies, we quickly found that our current design philosophy simply is not enough. We cannot continue designing our systems in the way we have been for years if we want to try to mitigate flooding for water quantity. And in fact, it doesn't even mitigate flooding from the 10-year event. If we do want to adapt, the most cost-effective strategy would more storage. We need to have storage throughout our system that can hold water, capture it, and let it out slowly. However, we recognize that many areas, and especially areas in the Chesapeake Bay region, are fully developed. You're fully built out. There are no new spaces to build new treatment practices, and land value can be very high. Therefore, in those areas, smart systems or adaptive level control systems can actually be very cost effective because you can retrofit existing storage to be a smart system that can increase and make more benefit out of your existing storage spaces. So that could be a low cost alternative, especially in areas where you have existing storage, whether that's wet ponds, underground storage, or other systems. Now, costs. I didn't get to cover costs because it takes a bit to talk about costs, but I can give you the overview. If you do nothing, if we use our existing infrastructure and we just put our heads in the sand and hope for the best, we still have to maintain that infrastructure. And that's, for our watersheds, at least in Minnesota, over a 20-year life cycle, was somewhere between $2 and $8 million for these relatively small watersheds. The cost of impacting or implementing our most cost-effective strategy, our more storage strategy, was somewhere between $20 and $50 million over that 20-year life cycle. It's really only a 6 to maybe 10 times more expensive than doing nothing. Now, excluding land costs are highly variable. It's not in the calculations. We talk about that in the report, and you can see what we recommended to do for land costs. But really, to increase capacity, the most cost-effective way that we know today, it's only 6 to 10 times more expensive than doing absolutely nothing. But a single storm event, that storm event I showed you in Duluth, Minnesota, costs about $100 million in damage. So we can choose. We can spend somewhere between 20 and 50 million. Again, these are all relative costs for our watershed sizes. Keep that all in mind. We can spend 20 to 50 million dollars over 20 years to create resilience in our watersheds, or we can do nothing and potentially lose $100 million in infrastructure in a single weekend. So it's all up to us. As stormwater managers, designers, planners, we need to be thinking about these things. We need to be building in resilience as much as we can. And there are numerous sources of resilient infrastructure funding available at the national level and local level. I don't have time to talk about that today, but I encourage you to go out and look for that because it is there. It can help you as you try to adapt your systems. If this was interesting to you, if this provided anything that was useful, I encourage you to check out our website. We also publish our Stormwater Updates newsletter, which then talks about much of our research that we're doing, including this project. All of our project reports, including the one I linked in the chat for this project, and all of our others are on there. It's our project reports, our publications, our other documents and guidance and resource tools are all available there. The QR code is there. The website is there. We can also drop that in the chat here in a minute. But we also use that Updates newsletter to talk about our Stormwater Seminar Series and announce the next speakers. This is an event that we've been doing since 2019, and what it's meant to do is bring nationally recognized experts in stormwater and green infrastructure to talk about a topic. And then we put them on a panel with local experts, to Minnesota at least, to talk more in depth. And really the whole purpose of this seminar series was to give you, the practitioners, the stormwater audience and industry, an opportunity to engage in the conversation, to ask questions and get answers from the best and the brightest in the stormwater world. We have another seminar coming up on August 1st. We're very excited to have Ryan Winston coming back to talk about bioretention. So if you're interested in that, again, go to our website, look at the schedule. The other thing that we do at this seminar is everything is recorded and on our YouTube channel. So if you see someone here that you would have really liked to see their presentation, it's recorded, it's freely available for you on our YouTube channel, and you can get professional development hours as well. So with that, I will thank you very much for your time and attention. Again, thank you to the Chesapeake Stormwater Network for inviting me to give this webinar. I'd be happy to entertain any questions you may have. Thank you so much.
Thank you so much, Andy. I will go ahead and stop the recording here.